my. Okay. All right, we're starting a new unit today. So today's warm-up is not based on anything you've learned, but something you can imagine. So imagine we have finished some type of assessment or you're handing in your homeworks, and I hand you a big stack of papers, and I ask you to sort those papers by name. I've given you a physical stack. If you go into the poll everywhere, I think I've picked the correct type of question where you can type in an answer. And if you see an answer you like, upvote it. Let's see who comes up with the most interesting or popular algorithm for how to sort a stack of papers you're holding. Go ahead and take 3 minutes, and we'll check back in. Okay, I think I can pop over and we can watch you. Let's see. Okay, let's see what happens. Ah, yes, a popular one right at the top, a very efficient algorithm. I call that the 52-card pickup of sorting algorithms. But go ahead, take another couple minutes. Let's see what we like best in here. Ah, yes, yes, of course. Why didn't I think of that? Interesting. We have a number of the stacks one popping up, the 26 piles. Interesting. Looks like a random sort continues to win. Though the anarchist in me is very compelled by the popularity of the second one here. Cool. All right, let's talk about some of our wonderful ideas. So toss them up in the air, randomly pick them up, and see if they are in sorted order. This is actually a named sort in computer science. Does anybody happen to know the name of these two sorts? Somebody wrote it in the list, so I know somebody in here knows what this one is called. Does anyone happen to know the name of it? Yeah. It is BOGO sort. So if you've ever heard of something called BOGO sort, it's actually kind of a joke. But it is the idea that one way to sort any collection of anything is randomly sort it and be like, is it sorted? No. Randomize it. Is it sorted? No. Randomize it. Is it sorted? Like I said, I call this a 50-card pickup. It's like throw it in the air and then gather it. Is it sorted? Throw it up in the air again. Does anybody want to guess what the run time of BOGO sort is? Yeah? Yeah, we would call that n factorial run time. So, as you can imagine, unlikely to be implemented, But I was on YouTube, a place for much learning and reasonable debate this morning, and somebody, the number one comment on a video about BOGO sort was like, technically, the best case scenario of BOGO sort is the fastest sort. And I'm like, oh, that is technically correct. If you took a set of papers and threw them up in the air and then gathered them and they were sorted, best case scenario. Also, I love this. Listen, if I was doing interviews for program management and you gave me this answer, I would hire you. Because the secret to making anyone in corporate America really impressed is to answer their question by totally redefining the question in a way that you can give a perfect answer and they can't rebuttal. So I think that's hilarious. Good job. A stack of 0 papers is always in sorted order. And you've burnt the evidence, so what are they going to do? Let's see. I think these are interesting. I saw a number that fell into this category. Sort by the letter of the first name into 26 piles. And then it's sort of like once you've split it into piles, maybe you're putting those piles like out on the floor or something like that, and then you sort within the piles. This is another type of sort. We're going to talk about that sort on Friday. Does anyone happen to know the name of that sort? I haven't taught it to you yet, so I wouldn't expect you to. This is technically what we would call bucket sort, which actually is arguably the fastest sort. Congratulations. That is technically the fastest we can do because it's a niche sort. We're going to talk about it. I also love this one. Give it to someone else to sort. I went back and watched my video of this from last year, and no one last year came up with this, which is kind of wild to me because we're using computers in this class, and if we should learn anything from computers is that they're really good at being told what to do, so just tell them to do your work for you. Find a lot of different computer processes and pass that along. That's what recursion is. So I love that. Yeah, correct. Absolutely. Also, when in doubt in an interview, hash map it. Sure, we love it. There we go, redefine it, love it. Interesting. There we go. Okay, look through each paper in order. And if it has a letter earlier than the last one, swap the two and do so until sorted. I was scrolling until I got to this one. Shout out to whoever put this in there. That's the one I would probably do. Because I'd probably try to hold all the papers in my hands, and then I'd look at the front one, and I'd be like, okay, I'm going to sort the 2 closest to me in relation to each other, and then I'll look at the third one, and I'll kind of like insert that into that sorted collection, and I'll look at the fourth one, and I'll kind of insert it into the next one, and I'm doing a really bad foreshadowing where I'm going with this. But these are great way to start to think about it. Okay, hang on. I'm going to exit out of presentation, and then I'm going to reactivate it, because I know how to computer. Okay, so here are some English descriptions of how you could do this with the associated computer science sorting algorithm, but I'm going to talk about each of these in turn. So this is mostly just for funsies to get us started thinking about the act of sorting things. Before we get too deep into it, announcements for today. Reminder, the Career Navigation Social event, as planned by our wonderful community team, will be happening immediately after lecture today. And I'm sure one of the TAs from that is here to walk you over. Maybe they'll come and I'll see them. Yes? Nope, just kidding. Nope. We'll see them hopefully soon. I think they're just going to talk about careers in tech, so come hang out. I think there's hot chocolate. Okay, also, welcome back from your long weekend. I hope you're all rested. Surprise, remember you have your final exam next week? I know it's weird because it's in week 9, but the thing I tell myself is that isn't it nice that you have a 1-hour exam instead of a 2-hour exam, and it's in week 9, so you don't have all your other stuff going on, and then we just get to talk about fun computer science stuff, and you have a little exercises to do, so this class can wrap up early, right? Yeah. Also, this is how we can do the thing where you can do your resub, because I wanted to give you that opportunity. So that's why our final exam is in week 9. We will talk in more detail about it on Friday. The TAs, of course, will be hosting their usual review session. There will be practice problems, all of that sort of good stuff. One thing to clarify is I think somewhere on the website it accidentally said that you have to type or you have to handwrite your notes. That's not true. I don't care. Type your notes, print out your notes, bring a textbook, whatever makes you happy. As long as it's not electronic, do whatever you want to do with your notes. Also, reminder, the P4 assignment is out. And if you want that extra credit bump, remember there's a separate assignment where it just asks you some questions that sort of shows you've read through the assignment. That extra credit piece is due this Friday. I wanted to crunch my throat lozenge and not subject the people listening on Panopto to that terrible noise. Okay, and then the midterm resubmissions are being graded right now. We are going to get those grades back to you, and then we will reopen the regrade request. So if you think you were incorrectly graded on the in-person midterm or the digital resubmission, we will open the regrade request for those simultaneously, mostly so the poor TA's brains can just focus on grading one thing at a time. So that'll open when we release those to you. Any administrative questions at this moment in time? Cool. Let's talk about sorting. Okay. So this course is called Data Structures and Algorithms. If you did not know, this course is called Data Structures and Algorithms at almost every single university that teaches computer science. In fact, pretty much every computer science program on the face of the planet has some type of introduction to programming followed by data structures and algorithms. It's one of the most ubiquitous courses, and typically the thing that recruiters ask, have you taken this class before you're eligible to apply to things? But so far, we've been really focused on the data structures portion, and usually at this time of the quarter, I get somebody that's like, where's the and algorithms part of this class? That's what we're going to be talking about today and tomorrow. We're going to be talking about algorithms in the context of sorting algorithms because we are proud nerds and we are just obsessed with sorting. I will admit I get sucked into it too. It's just really fun to think of all the different possible ways to accomplish the exact same thing. But that's not really the lesson of these 2 days. Because the reality is you're very unlikely to go about implementing a sorting algorithm just to implement it. But what we are really going to be talking about is how we evaluate algorithms for a different context. We've been talking about data structures in terms of, what's the run time to run any operation, how do they store things, what's the best scenario they're used for. Now we're going to apply that same sort of what's the best tool for the job type of thinking in terms of algorithms, and we're going to do that in the context of sorting. Okay. So there are 2 general categories of sorting algorithms, something called comparison sorts. This will be the vast majority of the ones we talk about. And they work by taking 2 elements that you are trying to sort in your collection and comparing them to one another at any given time, and then putting one before the other. The way that this is accomplished is by calling the compare to method. Now remember, the compare to method is a method that exists inside of the object. So if you write a new object, it's your responsibility to determine how to compare 2 objects. And this hopefully makes sense. Like, let's say you made a student object. It's up to you. Do we sort by the student ID? Do we sort by the last name? Do we sort by last name, then first name, so on and so forth? It's up to you to define how we compare 2 given objects. Then the second type of sort is something we call a niche sort. A niche sort is one that can't work on just any object, but rather works on a specific type of item where we can break apart any individual entry. So a comparison sort takes 2 items in the collection, compares them to one another. A niche sort pretty much only works for, say, integers or numbers where we can split them by digit, or strings where we can split them by character, and we'll compare within those things. This is kind of what you were doing with the 26 piles in the exams context, because you could split apart a name and look at the first letter and group things into a bucket. That's the name of the sort we're going to learn. Within that letter, and then sort within that. So these niche sorts can get super fast. They can actually run in linear time, but they're only good for sorting like numbers or strings. Comparison sorts can compare any type of object, that as long as it implements compare to, but I will tell you the fastest worst case scenario for any comparison sort is n log n. So you'll often hear engineers, when they talk about sorting algorithms, they just assume the runtime of a sort you're going to choose to use is n log n, because up until now, research tells us that's the fastest we can do. I'm going to teach you a few that run slower than that. I'm going to teach you some that can run a little faster than that, but that's kind of where we're at. Okay, I also need to give you a little bit of terminology. So when we are sorting items, we have to give you the items in some type of collection. Like I handed you an armful of exams, or I give you an array of values. If you take that collection and you sort it without needing any extra space, if you're still holding the exams in your arms and just kind of moving them around, that's what we refer to as an in-place sort. If I give you an array of unsorted items and you just kind of move them around within the array, you never make any new arrays, in-place sort. If instead you need extra space to store it, like I started to make piles on the floor, not in place. I needed extra storage in order to organize my thoughts. This is the one that confuses most folks. Stability. We are going to be talking about sorting. I'll mostly use numbers because I can only fit them on slides. But we're talking about sorting objects or complicated things, et cetera, et cetera. And so a stable sort is one in which after you've sorted things, duplicates on the aspect you're sorting remain in the same original relative order. What I mean is, let's say I ask you to sort this array of animal objects. And for some reason, these animal objects have a number and a string associated with them. And I ask you to sort based on the number. If when I sort based on the number, the two items that both are 8, those are the duplicates, remain in the same relative order they started in, that's stable. If they don't, that's not stable. And the reason that we care about this is that there might be multiple aspects to the object. So for example, you might have a situation where I ask you to first sort on last name, and I guarantee there are duplicate last names in this room. A stable sort will guarantee that the original order in which your names appeared will maintain in the sorted list. So maybe I want to run a sort on your last names, and then I need a predictable order for the first names within the last name category, something like that. We're going to look at it in more detail. I will also take this moment to shout out GradePage, which for some reason has an unstable sort, and when I submit your GPAs, it resorts within the last name totally randomly. Honestly, I can't believe no other professor has gotten crazy about the UW system that they use an unstable sort when we're filling out your GPAs, because it drives me nuts. And then, of course, the other thing that we are going to compare and contrast is the speed. Any questions on this so far? Okay, I'm going to talk about a subset of sorts, but there are a lot of sorts out there. And in fact, there are sorts that have been invented for, I don't even know what practical reason. I don't know, frankly, what a lot of these are. You know, we're going to talk about quick, and we're going to talk about merge, we're going to talk about heap. I don't know what postman or bead sort is, or simple pancake sort, but I literally just looked through Wikipedia and found everything that was considered a sort. I did look up rainbow sort, and that is the idea that you take your digital information and you transform it into a wavelength of light, and then you pass it through a prism, and then it uses the natural rainbow ordering to order the light, and then you retransform the light back into data. There is a YouTube video on it. You could go watch it. It is fascinating, but like when I say we're big nerds, I mean we're big nerds. We love sorts, okay? People inventing sorts just for the funsies of it. Maybe you can go out there and invent an absolutely insane sort, and then I'll add it to this list. But what do we actually care about in terms of sorts? Like I sort of mentioned, the point of this is really to talk about algorithm design and the different ways to compare algorithms. If you like what we're doing and want to do more algorithms, there is CSE 417, which is technically considered the following class after 373. You'll notice it's a much smaller class. It's a pretty theory-heavy class, but it's really going to get into algorithm design and stuff like that. So if you're into what we're talking about now, you can take that class. Okay, there are sort of 3 different algorithm design patterns, and we're going to use sorts to illustrate them. So the first is what we call sort of iterative improvement. I'm going to give you a collection, and you're going to run some type of loop or some type of iteration, and on each iteration, you move that data set one step closer to your goal. So maybe it gets just a little bit more sorted on every loop. That's one strategy. Another strategy is divide and conquer. Again, computers are really good if we split up our tasks and tell them to do smaller and smaller versions of the task. So that's like if I had my papers in my hands and I handed a bunch to each of you and asked you to sort them and then hand them back to me. Divide and conquer. And then the reason we do sorting here at the end of the quarter is because you've learned some data structures that inherently order the data based on how they sit in the structure. We can use those structures to just dump data in there and then pull it out and have a sorted collection. Okay, we're going to start with the iterative improvement one. And so the idea is that after k iteration of the loop, we will have sorted or changed the relative position of k elements. Let's start with something called insertion sort. See the foreshadowing. Okay, here's how insertion sort works. You have an array. It starts totally unsorted. So this subsection of the array, the entire thing is initially marked as unsorted. And then we look at the thing at the very beginning and we say, is it in the right position relative to these sorted items? If it is, we mark it as sorted, and then we grow the sorted portion so that we shrink the unsorted, we grow the sorted until we're done. So what we will do is as we loop over the array, for every new item we encounter, we ask ourselves, where does this belong in the relative order of the things I've already sorted? So that's the one where I'm holding my papers, and I look at the first name, and I'm like, oh, one item is sorted. And then I look at the second item, and I'm like, oh, is the second item smaller than the first item? If so, I would pick it up, and I would insert it into its proper position within the sorted, and then I'll look at the third item, and I'll pick it up, and I'll insert it to wherever it goes. That's where the insert comes from. So there you can see we were sort of looking at 5 as the thing to consider, and we would look through the rest of the things and we would realize, well, 5 belongs here between the 3 and the 6 comparatively, and then we'd move on to 8, and then 8 is right where it belongs, and then we would move on to 4, and then 4 we'd eventually pick up and have to insert way down here between the 3 and the 5. Casey, that's so hard to visualize. Oh, well, thank goodness that the internet is so fertile with so many visualizations. Before I show you the fun one, if I haven't shown you this yet or you haven't found it yet, this is a website called Visual Algo. It actually has visualizations for like all the graph algorithms we've already done and all that stuff, and it does all the sorting algorithms. But here is an unsorted, an unsorted list, and I have all these wonderful controls, and I can decide how fast or slow it goes. But if I just press sort, it is going to show you, see there, it's decided 6 and 31 were in the right relative order. 21 needed to swap with 31. That 1 was the new smallest item, so it got inserted there. I'm looking for the place for 6. It goes next to the other 6. And so you can watch this visualization, and you can see the sorted portion of the list is growing. And for each new item that's sort of right at the threshold between the unsorted and the sorted, I then loop over the sorted section and find where I should insert it until everything is sorted. Any questions on that visualization? But Casey, I still don't get it. Well, let me introduce you to some of the most incredible artists of our time. This is real. I'm sorry, it's a little dark on the screen. These are called the Algorithmics, and they are a troupe of Eastern European folk dancers, and they do folk dancing to represent all of the different sorts. So you can kind of see the ones that are facing us are the sorted list. The ones that are their backs turned are the unsorted. And as you can see, one just turned around, and now she's trying to find where she must insert herself into the list. And then she's like, oh, I'm good, clap. And then 8 turns around, and 8's like, it's my turn. Where do I belong in this list? Should I swap with you? Nope, clap, we're done. And it's 7's turn, and so on and so forth. I have placed, obviously, the superior visualization on each of the slides. You can watch the Algorithmics dance for each of the things we're going to talk about. Okay, actually, I do believe 8 and 2 have the best little jig here. Yes, get it. Aha. But then 2 has to keep going down the line, and so on and so forth. So, now that you have seen a few different visualizations of insertion sort, let's talk about how we want to analyze insertion sort. Okay, we did this, all right. Okay, can anyone tell me what you think the worst case runtime of running this sort algorithm is? And if you remember, we have to loop over the unsorted list to get to the new item we want to sort. And then once we're finding the thing we want to sort, we then need to loop over the sorted portion of the list to find where to insert it. And also because we've got an array, every time we insert something, we kind of have to make space for it by shifting everything. So does anyone want to tell me what they think the worst case runtime of this is? Yeah.
I was thinking about the worst case runtime.
Oh, please.
The worst case would
Yeah.
be if it's in reverse order.
Yes, if it is in reverse order, and thank you, that has brought up a good way to think about this. If it helps start to think about all of these sort algorithms, the worst case scenario is almost always reverse sorted order. So then what's the best case scenario? Already sorted. So if this is reverse sorted and every single thing needs to eventually get inserted and shift everything over, what is the worst case runtime? Anyone? Sure. Ooh, that is a great memory because I told you that's the best we can do, but I'm going to tell you this is an even less efficient model than n log n. But you're absolutely right for the ones we're going to get to after here. Yes? It is n squared, yes. We have a loop that's looping over everything, and then within each of those placements we're trying to find, we have to then loop over the sorted list and insert it and shift everything. So if you can kind of see here, we've got insertion sort for the entire list, shift, and then here we've got a for loop that goes over the entire thing. That's where our n squared comes from. So then do we have a difference between the worst case runtime and the best case runtime? And as our friend pointed out, will this algorithm run differently if the list is reverse sorted versus if it's already sorted? Yeah, please.
If it's already sorted, it could be O of n.
See, this is and I will tell you that there are definitely sorts that do that. But this one, annoyingly, still has to loop over everything. Oh, yeah, there you go. Oh, wait. Oh, I swapped the order. I'm sorry. I swapped the order of my slides. You're right. If it's already sorted, then what would happen with our little algorithmics is every time I'm like, it's your turn to find out where you should insert, they'll look to their neighbor and be like, I don't have to move, and then it ends. So you're absolutely right. If it's already sorted, it's going to go run linearly. And so we have a best case of linear runtime, a worst case of n squared. Kind of based on how much shifting you have to do to make space for it. But we consider this to have an in-practice runtime of n squared. If you're in an interview and somebody asks you what the runtime of insertion sort is, you should say n squared. Okay. Do we think this is stable? Do duplicates remain in the same relative order? Yeah? Are you raising your hand?
I want to ask a
Oh, sure, please ask a question. So if it is already sorted, it will run in linear time. It's just going to run in one pass, and every new item it encounters, it'll look to its neighbor and be like, do I need to like shift? No. And so I think of this one in the algorithmic terms, like each time somebody turns around and they do their little jig, they look to their neighbor and they're like, oh, I don't have to move, and they just stay where they're at. So that's going to be a linear pass. But most people don't believe that to be a very statistically relevant best case. So if somebody asks you in an interview or somebody's like, what did you learn in your data structures and algorithms class? You should tell them that insertion sort runs in n squared time. But it technically has that range between n and n squared. Yes?
So why doesn't the find spot add onto the loop?
Why doesn't the find spot? So find spot is actually going to maintain the index. Oh, I see. So it technically will run through, but it's only nested 2 levels. Are you asking why that doesn't turn this into n cubed time? Yes. So what it's going to do is it's going to loop over the other list, and you can see here it finds spot. That's inside the for loop. And then after it finds spot, it shifts. So it actually is sort of like 2n squared, but we dropped the 2, if that makes sense. So it's not n cubed. It's not triply nested loops. It's 1 outer loop and then 2 inner loops that are siblings. Yes? I would say it's stable. Yes, absolutely. And I think there was an example in the visual algo where like the 2 6s remained, and that's because we always kind of start with the new item and we compare it to its neighbors in the order. So we're always kind of keeping things relative to one another. So this is a stable sort. Is this an in-place sort? Do we just sort it in the array we were given, or do we need extra storage for this? Anyone? Yeah, sure. In place. Yes. So as you can imagine, since it has that really nice best case scenario, then this is a great sort to pick if you know you already have a mostly sorted list. Depends on your situation, right? Like maybe you start with a sorted list and then you're going to add rarely new items into it. You don't have to run sort that often. Maybe this is a good situation for you if you really care about space. Yes?
Is there ever a situation where like you're kind of weak and only like sort halfway, and as a result you reduce your runtime?
Thank you. What a good question. What if you only need, this is actually a type of problem we would call the top K sort. Like what if I give you a collection, I just need you the 5 smallest items in sorted order. So I don't need you to sort everything, I just need the 5 smallest. Will this sort work for you? After 5 iterations, are we guaranteed to have the sorted list be the ultimate final sorted list? No. But what an incredible segue. Also, here I have added some slides to prove the stability thing to you because I find that to be the thing that's most confusing for students. But this is a reference slide. I'll let you read it in your own time. Let's meet a new sort, selection sort. So selection sort, again, I give you an array of unsorted items, and you're going to maintain some section. It's going to initially start all unsorted, and the unsorted is going to shrink, and the sorted is going to grow. But what happens here is I'm trying to look at 18. I'm like, instead of asking myself, where does 18 belong in the sorted list, what I instead am going to loop over is the unsorted list to find the next number that should be in this location. So I'm going to realize as I loop over the unsorted items, 9 is the next smallest number still in the unsorted list, and then I'm going to swap it into that position. Then I look at 10, and thankfully 10 happens to be exactly where it should be. Great. And then I look at 14, and I'm going to loop 14, 18, 11, 15. I'll eventually realize 11, and I'll swap 11 and 14. So to our friend's question, this one, you could bail out early if you only needed, the first 5 sorted or something like that. The big distinction here with selection sort is instead of looping over in the sorted list to find something's position, I look at that sort of threshold between the sorted and the unsorted, and then I loop through the unsorted list to find the next available one. In my stack of papers example, that's like if I'm holding all of them and I just start looping through everything looking for the absolute first name in the alphabet, and then I grab it and I put it where it's supposed to be, and then I loop through the rest and I find the next smallest number and I put it where it's supposed to be. I'm sort of looking through the entire unsorted list and selecting which the next sorted item is supposed to be. And again, I'm constantly looping through the unsorted list and growing the sorted list. Great. So here is our selection sort, and you can see we have that same outer for loop that loops over everything. And then inside, we have that find next min. That's sort of the inverse of the find spot, but it's still looping over a portion of the array, right? So I'm looping over the unsorted portion of the array to find the next min, and then I swap that item with the position I'm considering. So we don't have to do shifting in this case, which is convenient, but I still have this find next min loop inside of this for loop that runs over the entire thing. So what do we think the worst case runtime of this is? It's a nested loop. N squared. Okay. Now, here is the thing. Our previous one, we were just kind of, because of the shifting nature of it, I could really quickly determine if I had to continue looking through the sorted list. But now, because I'm looking through the unsorted list, I don't know if I'm going to encounter another smaller item. Every time I go to find the next min, I always have to go all the way to the end to see if I can find any number smaller than the one I'm considering. So what's the best case runtime of this? Is it any faster if the list is already in sorted order? No. Thank you. And that's where my brain was, because I practice these in inverse order. So this one has the same best case and worst case scenario. But if you wanted to split hairs, technically it has one fewer term of n inside of the nested for loop. So this is truly n squared instead of like 2n squared, if the coefficients make sense to you or matter in your context. Is this an in place, or in practice, it's n squared, whatever. Is this a stable sort? Are things going to remain in the same relative order? And I would give you a hint to think about that swapping nature. I'm seeing a bunch of head shaking. I agree with the head shaking. This is not a stable sort. And actually, anytime you have that sort of swapping, it's kind of like I'm looking at a position, I'm like, who's the ideal occupant for this position? And if it's not who's already there, then just get them out of the way. Like, send them wherever the other thing is. I don't care. And because of that, I'm messing up the relative ordering, so this is not stable. Anytime you have swapping, it's unlikely to mean that you'll have a stable sort. What about in place? Do I need any extra storage to do this? No, this is in place. Great. So, yes, this is useful for top case sort, especially if you can't use any extra space. Any questions on selection or insertion sort? Yes, please.
What if you had like an unordered list that was in reverse order? Since that would be worst case for both selection and insertion, you said that in selection, the worst case, the constants are better in worst case, so would we be using the selection sort instead of the insertion sort?
This is a good question. Let's say you have an array of a totally reverse sorted order. Would you pick selection or insertion sort? Anyone want to take a guess at it? They technically are in the same complexity class, but there's a difference. The coefficient of the n is different. Yeah.
Selection sort.
I agree. I would pick selection sort. Also, too, because the swapping, as opposed to all of the shifting, those are all sort of coefficient benefits to selection sort. So you'll find selection sort is maybe a little more popular in that context because the constants are better. I would pick insertion if you've got that like possibility of staying closer to sorted order. Yeah.
Can you explain again why the best case runtime is n squared?
Sure. So it's n squared in this case because what's going to happen is I have an overall loop that's going to start and loop over the current item. So the current item's my outer loop. My inner find next min loop always has to loop over the unsorted list because what I'm looking for is what's the next smallest number. And I can't be guaranteed to know if I found the smallest possible next number until I actually look at absolutely everything. The reason that disappears in insertion sort is because I'm looking in the sorted list. So when I look at my neighbor, if I'm already bigger than my neighbor, I know I don't need to keep looking any further. But in the unsorted, I don't know where that thing's going to be. So I got to look at absolutely everything. Yeah?
Do you have like different sorting methods based on the type of data structure? Like this is an array. What if it was like a list?
So, great question. What if there's different types of structures? You'll find that pretty much most of the things here we're going to store them in an array just because we get that like speed up from navigating within an array. Remember all that contiguous memory goodness? But we are going to use some other data structures to sort, but spoiler alert, they're all those data structures that you can secretly use an array as the underlying storage because of all of those benefits. Yeah?
What is top K sort?
So top K sort is just a umbrella term for a common problem in computer science, which is I'm going to give you a collection of, let's say, n numbers, but I only need the K smallest. So I give you 300 students, and I ask you to give me the ones with the 5 students with the best GPA. So I don't actually need you to stack rank everybody, I just need the top 5 kind of thing. Again, here is an example for you to walk through so I can prove to you that this is not a stable sort. Okay, I got to get through one more sort before we leave for today. And we are going to move into the second principle, the divide and conquer principle. Where what we're going to do is we're going to start with a sorted list. We're going to start with an unsorted list. We're going to break it into small pieces. We're going to transform those small pieces into sorted lists, and then we're going to recombine them. Hint, it's recursive. Welcome to merge sort. Okay, so the way this works is I'm going to give you an unsorted list, and you're going to be like, whoa, is there more than one item in that list? Set those papers on fire, because a list of 0 is always sorted. It's that same mentality. If I give you anything more than a single item, you're like, I don't know how to sort that. So you're going to break it in half. And then you're going to call merge sort on each of those 2 halves. And if each of those 2 halves have more than one item, you're like, whoa, I don't know how to sort those. And you're going to break it apart and break it apart until you get to a bunch of individual lists of one item. And a list of one item is sorted. So we're like, sweet, done. And then you're going to, when you unroll the recursion, take 2 of those piece lists and ask which one comes before the other. So you're going to break this apart until you get to individual items, and then you're going to sort them on the way back up. So you divide without any logic, but you conquer with the sorting logic. So here's the divide step. Break it apart, break it apart, break it apart. Guess what? It's the magic of recursion. We pass half of the list into one recursive call, the other half of the list into another recursive call, and we keep calling recursives and recursives until we get to a list of 1. Then, when we unroll the recursion, we take back those 2 lists, and we know that they're already in sorted order, and then we ask, well, we're just going to start at the front of each list, and we're going to look at those 2 items and ask which one's the smaller. So here I'm going to compare 2 and 1, and I realize 1 comes first, so I move my arrow. Now I'm going to compare 6 and 2. I realize 2 comes first, so I'm going to move my arrow. Then I'm going to compare 8 and 6. 6 comes first, so I'm going to move my arrow. Then I compare 7 and 8. 7 comes first. I compare 8 and 55. 8 comes first. I compare 22 and 55. 22 comes first. And so on. And what happens here then is I only need one linear pass through each of these already sorted lists to interweave them together to a final sorted order. So this is a linear runtime as we put these back together. So let's say we start with this list of 4 items. We're going to split it into 2 items of 2. We're going to split each of those into items of 1, and then we recombine them, and then we can recombine them until we have a finally sorted list. Yes? I love that you brought that up on the slide. Yes, as you can see, what I'm doing, and you can kind of see this here in this pseudocode too, is if the list is length of 1, return list. That's my base case. Otherwise, make a new array from 0 to the midpoint and merge sort that half. Otherwise, make a new array from the midpoint to the end and merge sort that half. So because of this call to new in each of these recursive calls, and you can kind of see, look at how many new arrays I had to make. So to our friend's point, this is not an in-place sort. Okay, the runtime for this, it is recursive. And do you remember back in week 2 when I was talking about how to analyze recursive code, and I was like, there's 3 recursive patterns, and one of them is like divide and conquer, and I actually showed you merge sort as my example of that, and I was like, this is silly because I'm not going to teach you merge sort until week 8. Here we are. Okay, let's see if we remember recurrences. So remember, recurrences are that big curly brace where the top branch is the base case runtime. What is the big O of the base case of merge sort? O of 1, constant. Right. Now we're in the recursive branch. That's on the bottom. And we need to ask ourselves 3 things. What is the runtime of the non-recursive work that happens to exist in the recursive case? How many recursive calls do we make? And how do we transform n into each of those recursive calls? So that, thankfully, we have these 3 lines of code here. So right here, I'll say this merge line here, where it takes the smaller half and the larger half, that was the interweaving thing that I was doing on the previous slide. What's the runtime of that, of just putting the 2 sorted lists together? Yeah, n. So our non-recursive work in the recursive method is n. How many recursive calls are there? 2. That's the coefficient. How does n change in each of those recursive calls? N over 2. There's our recurrence. Do we kind of remember this? Dusting off some cobwebs. Spoiler alert, you may be asked to, analyze code on the final exam. So I'm trying to remind you of these wonderful things. Also, I know this doesn't fit in all of our magical stuff, so let's pretend I did the algebra for you. It's n log n. And in fact, merge sort becomes the classic, the diva, really, of the sorting algorithms. Like maybe merge sort's like the Whitney Houston, like still undeniably good, pretty much the best there could ever be, foundationally the best sort. Best case, oh yeah, thank you. Best case runtime, the same. In practice runtime, the same. Because I have to split apart and interweave, so no matter the order, merge sort runs in the exact same runtime, which is n log n for every single time, and because of that, you will find that merge sort for a long time used to be like the default answer for which sorting algorithm to use. Foreshadowing, we have better options now, and I'm going to show them to you in future classes, but before we get there, since we have a couple minutes, what about stability? Do we think this could be a stable sort? Am I comparing things still in the same relative order? Do I ever get them out of order? This one's a little harder. So I'm going to be honest with you. There are multiple implementations of merge sort, and there is a merge sort where you don't maintain stability, but you can write this one actually so that it is stable. And that's because when we do that interweaving thing, when we're bringing things back together, those things are still in the relative order, as long as we make sure that we write it the right way. Is this an in-place one? No, we talked about that. Kind of memory expensive. But you will find, like I said, that this is actually so wonderfully predictable, and because it has a predictable runtime and exactly the best possible runtime of any comparison sort out there, n log n, this is actually one of 3 sorting algorithms that Java uses when you call arrays.sort. Questions? Okay. I didn't get to quicksort, but it's okay. Go to section tomorrow because you definitely are going to want practice with these because exercise 6 is all about sorting algorithms, and we will come back on Friday to talk more about the more exciting and modern sorting algorithms. Thanks so much, everyone.